Hello everyone, in this video we're going to learn about ions and ionic compounds, as you might remember from previous video and also from reading the textbook and doing homework. Atoms in their neutral state have the same amount of electrons as they have protons, but that's subject to change. Some atoms would like to lose electrons and become positively charged, so known as cations, where the other ones want to gain electrons and become negatively charged. Generally speaking, metals like to lose electrons and non-metals like to gain electrons. But why electrons and what not protons? Because protons are embedded in the center of the atom, in the nucleus, they're hard to reach. But electrons, as you already know by exploring the atomic theory, are placed around the nucleus in quantized levels of energy. The most accessible ones of these layers is the outermost one, also known as the valence layer. So the electrons in the valence layer are subject to removal or to be added to. For example, sodium could lose its only one valence electron and become positively charged sodium. There are other examples. Magnesium could lose 2 electrons in its valence layer and become magnesium 2 plus. Whereas oxygen could gain 2 electrons, become O2 minus, and fluorine could become F minus. But how do we predict the amount of electrons lost or gained by all these elements in the periodic table? Is there a formula? Well, yes, you could follow this trend. So all the group number in every group reflects the number of electrons in the valence layer of the neutral atom. So group 1 elements have 1 electron in the valence layer, group 2 has 2, all the way to group 8 that have 8 electrons. I'll have to excuse the transition metals, which are the metals in between from groups 3 to 12, which do not follow that trend. They have their own set of rules. They have their own mind. They decide how many electrons they want to lose. Sometimes, as you can see, they can acquire multiple charges instead of a single charge. So we'll have to discuss them later. But in the main groups, which is groups 1 to 8a, you can say that all the elements in group 1 would like to lose 1 electron and become +1. All the elements in group 2 would like to lose 2 electrons and become +2. You skip over transition metals. 3 plus is the charge of all the elements in group 3. Group 4, although it says C4 minus, but you rarely see a C4 minus or a C4 plus. They're kind of in the middle. If they want to gain any electrons in their valence electron, which is the octet rule, the requirement, they will have to lose 4 electrons, which is not that easy, or gain 4 electrons, which is not that easy either. That's actually the basis of the organic chemistry. So we'll put a tentative 0 there, indicating that, hey, we don't really see a lot of charged carbons, whether it's positive or negative, until we heat organic chemistry. And that 0 also acts as a mirror. It mirrors all the charges that preceded the 0. So now they're in the negative territory. Group 5a would like to gain 3 electrons and become 3 minus. Group 6 would like to gain 2 electrons and become 2 minus. Group 7, 1 minus. And group 8 does not gain or lose electrons as well, also known as noble gases. So this is a very valuable trick to memorize, to predict all the charges of a 2B ion, whether it's going to be plus or minus. So these are known as atomic ions because, well, it's just one atom gaining or losing electrons and becoming an ion, but there are molecules that could acquire a communal charge, but for example, and they are known as polyatomic ions. Polyatomic ions are molecular ions, molecule that carries a charge. Because molecules, as we know, are neutral. But what if it's charged? Well, it becomes an ion. And there's a list of some of them. Is there a formula? Is there a rule that you can memorize all the charges and all the names? Unfortunately, the best way to memorize them is to explore them, establish mini trends for yourself. But long story short, you have to memorize them. The ones on this screen are the important ones, so I suggest you memorize them. But you can see mini trends in them. For example, in the chlorates, right? If it has 4 oxygen, it's a perchlorate. If it is 3, it's chlorate, chloride, and hypochlorite. So if you follow that trend, you can see per means even more, and then hypo means even less, 8 means more, and ite means less. Oxygens, you can discover these kind of trends, but my suggestion to you folks is to put maybe 30 minutes to explore these molecular ions, memorize their charges, their formula, and their name. All right, let's discuss ionic compounds. We said, hey, some ions mostly, some atoms mostly metals would like to lose electron, become positively charged, but the other ones have to gain electrons and become negatively charged. So what if two of them meet? What if a metallic ion meets a non-metallic ion? Can there be an exchange of electrons there? Yes, the electron transfer would behoove both of them, right? Sodium wants to lose one electron, fluorine wants to gain one electron. So why not just fluorine? Why doesn't sodium just lose its electron to fluorine? And that's exactly what happens. But once they become charged, oppositely charged, opposites attract, so they can form an ionic compound where electrons are fully transferred and ions are the constituting components of that compound. Well, what if there is not a one-to-one ratio to electrons? What if you have calcium that would like lose two electrons, and chlorine, which is a group 7 element, and would like to gain one electron? Well, then you have to offset the charges by the number of ions. So every 2 chlorine ions will offset the charge of 1 calcium ion. So the final compound would be calcium with 2 chlorides. So calcium chloride would have a CaCl2 formula. So let's practice that with the following questions. What is the formula of the compound that is formed between iron 3 and carbonate ions? Well, this is carbonate ion, CO3 2-, and that is the iron 3 ion. How do I know carbonate ion is CO3 2-? Again, I have memorized a bunch of useful polyatomic ions with their charges and formulas. Why does it say iron 3? Why is the charge specified? Because iron is a transition metal, and some transition metals are capable of having multiple charges. Iron can have a 3+ charge or a 2+ charge, ferric or ferrous ion. So it's important that if you're dealing with a transition metal capable of having more than one charge, you have to specify what the charge is, otherwise it's going to be ambiguous. So what is the charge? What is the compound formed between iron 3+ and the carbonate ion? You can say that for every 3 carbons, you can have for every 2 carbon ions, you would need 3 carbonates in order to charges to be fully offset. Is there a quick way to know that? Yes, you can use iron's charge as a prefix, as a subscript for carbonate, and vice versa. So iron's charge could be a subscript for carbons, and carbonate's charge could be a subscript for iron in the newly formed product. Another example would be magnesium and fluoride. What is the magnesium ion's charge? Magnesium is in group 2. That means it's going to be Mg2+. Fluorine is in group 7. It will become fluoride, right? F-. So again, you can cross multiply the charges for the subscripts. Magnesium is 2+, so that means fluoride's charge would be F2. Fluoride's charge is 1-, that means magnesium subscript would be Mg1. How do we name these? Very important. If you are dealing with a fully atomic ions, which is the case with magnesium fluoride, magnesium ion's name remains unchanged. Magnesium in its metallic form or magnesium ion are both known as magnesium. But it's the name of the anion, the negatively charged compound ion, that is going to be changed. So you no longer have fluorine, you have fluoride, IDE. So if you have an atomic anion, it ends with "ide." The suffix is "ide." Fluoride, chloride, oxide, nitride. If it's a monoatomic ion, an anion, it's going to be "ide." If it's a monoatomic cation, positively charged ion, it does not change. But for polyatomic ions, you don't have to do anything. You pretty much have to sew them together. Cation comes first, anion comes second. So if you have iron 3 carbonate, iron 3 carbonate. It's iron 3 making a molecule with carbonates. Making a salt with carbonate. So iron 3 carbonate. We can practice some of that naming for the following salts. How do I know this is an ionic compound? Well, I see a metal and a non-metal component. I see sodium ions and carbonate ions. So it's going to be sodium carbonate. I see sodium and hydroxide ions. It's going to be sodium hydroxide. Magnesium and bromide. Magnesium bromide. Potassium and chloride. Potassium chloride. Iron 2 chloride. Iron 3 chloride. Why do we have to specify? Iron 2
is going to make a different complex than iron 3 does. Iron 2 needs 2 chlorines to offset its charges, whereas iron 3 needs 3 chlorines. That's what they engender 2 different salts. A zinc hydroxide, zinc is a transition metal. But why do I say zinc 2 hydroxide? Because zinc is a transition metal that is capable of having only 1 charge. Beryllium, chromium, and aluminum are different examples as well. If you want to test yourself some more, you can do the following question, and the answer to this question could be found at the end of the slide deck.